Good morning, students, and most welcome in the chemistry class. I, Mrs. Janvi Banerjee, chemistry teacher of DAV 6, is going to start the electromagnetic radiation of the chapter Structure of Atom. Students, the previous day I have given the introduction on electromagnetic radiation. And you know, students, in 1900 Max Planck studied black body radiation and realized that to explain the energy spectrum, he had to assume that energy is quantized and light has particle character. Planck's equation is equal to h into nu or equal to hc by lambda, and h equal to Planck's constant, and its value is 6.626 into 10 to the power minus 34 joule into second. Wave nature of light. The fourth variable, light, is velocity. All light has the same speed in vacuum, that is c equal to near about 3 into 10 to the power 8 meter per second. It is the speed of light, everybody knows. The product of the frequency and wavelength is the speed of light. So c equal to lambda into nu. So lambda equal to wavelength and nu equal to frequency. So frequency is inversely proportional to wavelength. So frequency is inversely proportional to wavelength, my dear students. So from this you have learned the velocity of light, that is 3 into 10 to the power 8 meter per second, and the wave nature of light from this, the mathematical expression, that is c equal to lambda into nu. Wave nature of light, electromagnetic radiation can be categorized in terms of wavelength or frequency. Visible light is a small portion of the entire electromagnetic spectrum. There are different types of rays: gamma rays, X-rays, ultraviolet rays, microwave, so FM, radio waves, long radio waves, and the visible spectrum, that is the wave nature of the light. The particle nature of light, photoelectric effect. So light striking a metal surface generates photoelectrons. The light's energy is transferred to electrons in metal. With sufficient energy, electrons break free of the metal. Electrons given more energy move faster when they leave the metal. Students, in the live class, I explained the photoelectric effect. Now you see the particle nature of the light, that is photoelectric effect. It means that when a beam of light falls on the metal surface, it will eject the electron, and the energy of photon distributed in the two energy. One is the threshold energy and another is the kinetic energy. Threshold energy is the energy which is required to eject the electron from the metal surface, and kinetic energy means the energy that is given to the electrons. So kinetic energy plus threshold energy is equal to energy of the photon, and this is explained in the particle nature of the light. So light has wave character c equal to lambda into nu, and light has the particle character, my dear students. Particle nature of light, photoelectric effect is used in photocathodes. First of all, light strikes the cathode at frequency nu. At frequency nu, electrons are ejected if nu exceeds the threshold value, that is nu naught. Electrons are collected at the anode. Just you see, students, the particle nature of light and how electron ejected when the rays of light falls on it. This is very, very important things, and the photoelectric effect is based on the particle nature of the light. Neon lights emits an orange-red colored glow. This light has a wavelength of 670 nanometer. What is the frequency of this light? So this is very, very important question. Example problem 6.1. We know that c equal to lambda into nu. Therefore, nu equal to c by lambda. So velocity of light is 3 into 10 to the power 8 meter per second. So put the value of c, and lambda value is given 670 nanometer, and 1 nanometer equal to 10 to the power minus 9 meter. So put the value 670 into 10 to the power minus 90 in place the value of lambda. Particle nature of light. The photoelectric effect is not explained using a wave description, but is explained by modeling light as a particle. Wave-particle duality. Depending on the situation, light is best described as a wave or a particle. Light is best described as a particle when light is imparting energy to another object, and particles of lights are called photons. So light is the collection of photons. Light is the collection of photons. So one thing just you have learned here, light is best described as a particle when means light is imparting the energy to another object. Just you have seen in the photoelectric effect, light is imparting the energy to eject the electrons. So it explains the particle character of the light. Photoelectric experiments. For nu greater than nu naught, the number of electrons emitted is independent of frequency. Value of nu naught. What is nu naught? It is the threshold frequency. As light intensity increases, the number of photoelectrons increases. As frequency increases, kinetic energy of the emitted electrons increases. The kinetic energy of emitted electrons is independent of light intensity. So this is very, very important thing, students. A, B, C, D. For nu greater than nu naught, the number of electrons emitted is independent of frequency. Number B, as light intensity increases, the number of photoelectrons increases. Number C, as frequency increases, kinetic energy of the emitted electrons increases linearly. And fourth, the kinetic energy of emitted electron is independent of light frequency, independent of light intensity. Just you have seen the graphical representation, and it is explained A, B, C, D. And particle nature of light. The energy of photon is proportional to the frequency and is inversely proportional to the wavelength, that is equal to h into nu, that is h into c by lambda. The wave character c equal to lambda into nu, and particle nature equal to h into nu and h into c by lambda. So this is the mathematical expressions, the particle nature of light. Students, particle nature of light, the binding energy, energy holding an electron to a metal, threshold frequency, minimum frequency of light needed to emit an electron. What is threshold frequency? It is the minimum frequency of light needed to emit an electron. And for frequencies below the threshold frequency, no electrons are emitted. This is very interesting things. Frequencies below the threshold frequencies, no electrons are emitted. For frequencies above the threshold frequencies, extra energy is imparted to the electrons as kinetic energy. So E photon is equal to binding energy plus kinetic energy. And binding energy, it means the threshold energy. It is also known as the work function. So this explains the photoelectric effect. The laser in a standard laser printer emits light with the wavelength of this nanometer. What is the energy of photon of this light? So equal to h into nu, and nu equal to c by lambda. So lambda value is given here, c value you know, h value Planck's constant, 6.626 into 10 to the power minus 34 joule into second. This you have to put and do complete these numericals. Now students, Bohr atom, that is the Bohr models, J.J. Thomson models, Rutherford's models, Bohr's model. Now we are going to explain the Bohr's model. Electrons orbit the nucleus in stable orbits, although not a completely accurate model. It can be used to explain absorption and emission. Second, electrons move from low energy to higher energy orbit by absorbing energy. Third, electrons move from high energy to lower energy orbits by emitting the energy. Fourth, lower energy orbits are closer to the nucleus due to electrostatic force of attraction. And ground state. What is ground state? Ground state, the lowest state where the electrons are initially present, is called the ground state. An excited state, the state where the electrons on gaining energy subjected to go to a higher energy level, is called the excited state. Atom returns to the ground state by emitting energy as light. So ground state is the state of the electrons in the initial state. An excited state, that is the state of the electrons after gaining certain amount of energy. And when the electrons back from excited state to the ground state, it emits the energy as light. Atomic spectra and the Bohr's atoms. The Rydberg equation is an empirical equation that relates the wavelength of the lines in the hydrogen spectrum. And according to Bohr's atom, 1 by lambda equal to R into 1 by N1 square minus 1 by N2 square. R is the Rydberg constant, and 1 by lambda equal to nu bar, that is wave number, and R Rydberg constant value 1.097 10 to the power 7 meter inverse. N refers to the numbers of the energy levels in the emission spectrum of hydrogen. Atomic spectra and the Bohr atom. Example 4.8. What is the wavelength of light emitted when the hydrogen atom energy changes from n equal to 4 to n equal to 2? So just you have seen that is 1 by lambda equal to Rydberg constant into 1 by n1 square minus 1 by n2 square. Here n2 equal to 4 and n1 equal to 2. When the hydrogen atom's energy change from n equal to 4 to n equal to 2, so n1 equal to 2 and n2 equal to 4. So 1 by n1 square minus 1 by n2 square. So Rydberg constant value 1.097 into 10 to the power 7 meter inverse, 1 by 2 square minus 1 by 4 square. So 1 by lambda equal to 2.057 into 10 to the power 6 meter inverse. So lambda value equal to 1 by 2.057 into 10 to the power 6 meter. So this is the very important questions regarding the atomic spectra and the Bohr's atoms. 1 by lambda equal to R into 1 by n1 square minus 1 by n2 square. My dear children, all formula you will write in your assignment or classwork copy, and the related numericals you have to practice more and more. Atomic spectra and the Bohr's atoms. In 1913, Niels Bohr incorporated Planck's quantum theory into the hydrogen spectrum explanation. Here are the postulates of Bohr's theory. Atom has a number of definite and discrete energy level in which an electron may exist without emitting or absorbing the electromagnetic radiation. As the orbital radius increases, so the energy 1 less than 2 less than 3 less than 4 less than 5, that is k orbit energy is less than L, L than M, M orbit energy less than N. An electron moves in a circular orbit about the nucleus, and its motion is governed by the ordinary laws of mechanics and electrostatics, with the restriction that the angular momentum of the electron is quantized, can only have certain discrete values, my dear children. Light of characteristic wavelength is emitted when electrons move from higher orbit to lower orbit. Light of characteristic wavelength is absorbed when electrons jump from lower orbit to higher orbit. This is the origin of the absorption spectrum. N equal to 4, N equal to 3, N equal to 2, N equal to 1. That is energy. electrons when jumps from lower orbit to higher orbit, that it absorbs the energy, and when electron jumps from higher orbit to lower orbit, it radiates the energy. Atomic spectra and the Bohr's atom. Bohr's theory correctly explains the hydrogen emission spectrum, but the theory fails for other elements because it is not an adequate theory. So this is the drawbacks of the Bohr's theory. Students, up to this, next day we will discuss the de Broglie's concept, Heisenberg uncertainty principles, etc. Up to this, thank you and have a nice day.